Thank you for coming to the talk. It's called Make Classes Great Again. My name is Vinny Falco. I'm the author of Boost.beast, which is an HTTP and WebSocket library that's built on Boost.asio. It was accepted into Boost on July 20th. It will appear in Boost 1.66, which is scheduled for release in December. I'd like to say a few words about Boost. Boost is a wonderful collection of peer-reviewed, high-quality C++ libraries. If you've ever used features of the standard library, such as shared pointer, thread, or mutex, you should know that these features got their start in Boost. They predate their appearance in the standard library. The authors published their code into Boost, and that enabled them to get valuable feedback on their classes. They can fine-tune it with feedback from users. Users got some experience using the classes, and then they were able to write up a nice proposal to add it to the C++ language, because once it gets in the standard, then it's baked in. There's no changing it. So it's a really nice way to make sure that you've got something that's solid, that's well polished. That's the process that I think is the best for getting things into the standard. Now, during the Boost formal review process, you submit your library, and a bunch of people, usually smarter than me, look at your code, and they might say some things. Hopefully they'll say nice things. They'll give you a critique of your code. Sometimes it can be very honest. But no matter what, you're going to walk away knowing more about your library, getting a better idea of what you can do to improve it. If it's a really good library, then it'll be accepted into Boost. Here's an interesting fact. More people have been to outer space than have gotten their libraries into Boost. Okay. So during this talk, I'm going to give you a quick primer on HTTP, nothing too deep, just a light introduction. Then we're going to create a message model in C++ to model those HTTP messages. We're going to define some concepts. We're going to write documentation on those concepts. And we're going to create meta functions to check that types meet those concept requirements. So, HTTP. HTTP is the technology that powers the World Wide Web. It allows computers to talk to each other. It divides computers up into two categories. You've got clients and you've got servers. Clients you're familiar with, browsers are clients. There are command line tools that are HTTP clients. And then we have clients that you might not think of as an HTTP client, like this Samsung Smart Refrigerator. If you run low on groceries, it can order from Amazon, now Whole Foods, and it uses HTTP. The clients talk to servers. Server is a piece of software that runs. You've probably heard of Apache. It's an open source server. These HTTP servers run on a variety of hardware, from data centers to small devices like this Linksys router. If you open up your browser and you connect to your Linksys by putting in the IP address, and that page comes up so you can administer your router, that's a small HTTP server. So, in order for HTTP to take place, the computers need to be connected. The client, in this example, in the browser, they put in the domain name. The client performs a DNS lookup to retrieve its IP address, and it makes a connection to the server. So now that the connection is established, the HTTP conversation can take place. The client sends a message to the server. That message is called an HTTP request. The server processes the message, it does its thing, and then it sends back something called an HTTP response. So an HTTP request looks like this. Now, the first thing that you notice is that it's text. It's a readable protocol. It was designed a long time ago. There's some words in it that you might recognize. That first line is called the request line. It contains the verb, get, the thing that you want to do. Then the target, index.html, that's you want to get that file, presumably, and then a version, which is useful. After the request line, we have some name-value pairs called fields. And again, it's text. You can see user agent is the name, and then there's a colon, and then Chrome is the value. Now, the field names are case insensitive. That's important. We're going to come back to that later. So that's the request. A response looks very similar. Again, it's text. We've got the first line is called the status line. It's a little tiny bit different. It's got the version, and then a numerical code. 200 means OK, which is like an error code. It means everything went well. There are other numbers like 404, which means not found. 500, server error. And then we have a human-readable piece of text that mirrors the error code. That's for people to help debug. It's not really used very much. After the status line, again, we've got some fields. We've got the name-value pairs. And the name can be almost anything. The values can be anything. It's really defined by the semantics of the message. In this case, we have something called a body. So this is a body of the message. Any HTTP message can have a body. It's optional, doesn't have to be there, but this one has a body. Here it consists of text. You can see some HTML that's in the body. It could be binary, or it could not exist. It all depends on the semantics. Now, at this point, the object-oriented minded folks in the audience are probably thinking, well, hey, requests and responses are just special cases of a more general concept called a message. And you'd be right. So an HTTP message consists of the start line, which is a little bit different for requests and responses, then the fields, which are the name-value pairs, and finally, an optional body. The start line and the fields are collectively referred to as the header, and the rest is called the body. So, what do we want to do? We would like to model these HTTP messages in C++, presumably using some type of class. We want to be able to inspect the attributes of a message. We want to be able to change the attributes of a message. Now that we have our message container, we want to create some algorithms that operate on the container. We'd like to be able to serialize the container, which means turns the in-memory representation into the network format, that series of bytes, that text that you saw. And then we'd like to parse that message, which means take the bytes that come from the network and turn them back into the in-memory representation, which is in our class. So, I'm going to take a stab at making a message container. Here it is. This is a request. You can see the elements of the message. There's a version. We have a couple of strings for the method and target. And then we have the fields. Here I used a map. It's a map of strings. We're mapping the names to the value. Looks pretty reasonable. Then we have the body. Now, the body can be binary or text, and standard strings are perfectly capable of representing binary. You can put nulls in a string. You can have a string that's 0 length, which we could use to indicate that there's no body present. You can have unprintable characters. String is a very capable container for this sort of thing. So that's our request. Similarly, we can create a response. It's very similar, not quite the same. There's two things that are different, the status and the reason, but otherwise it's the same thing. So now we've modeled HTTP messages. We're done. Great. Okay, what's the problem here? Would anyone like to venture a guess? What's wrong with these declarations? Just think about what's wrong. Okay, so if you thought about any of the things on this list, well, there we go. So the first problem is that these containers are not allocator aware. So they're using the default allocator, which is probably good for most cases, but for special cases, it's not going to work very well. We don't want to just create a container. We don't want to create a good container. We want to create a great container. And great containers need to allow you to specify the allocator. Otherwise, certain people, such as the folks in study group 14, low latency programming, they're not going to be too happy with this container because they want to specify the allocator. The next problem is that the body is stuck at string. Now that's a good choice for most of the time, but it might not always be the thing that you want. Maybe you want a vector, or perhaps if you work at a large company like Facebook, you've got your own string that's optimized for your own needs. You can't use it here, so they're not going to be too happy with this container. Next we have the map. So the choice of map, kind of arbitrary. Maybe we want an unordered map. We don't have a choice because we've already made that choice for the user. Now, the declarations that we saw do not account for the case-insensitive nature of the field name comparisons, so we've got that problem to deal with. Finally, the request and response types that we saw, they're distinct. There's no relationship between those types. So, if we want to create a single function that is capable of serializing a message, such as this function called write, we have to make the parameter for the message a template type. So this signature will allow us to accept a request. It will allow us to accept a response. But it will also allow us to accept things that are not requests or responses, like a foo, or worse, an int. So the user can try to call that function. The compiler will be very happy to match it in the signature, but then it will probably get a compiler error, and a very long one at that, and it's not going to do the thing that we want to do. So that's not very exciting. The first thing we need to do is refactor the declaration for this container to resolve the issue of the unrelated types. So I've done that here. I've created a class template. That's where all the trouble starts. So here I've got the message class template, and you can see I've chosen to parameterize the class on a bool. Bool is a very logical choice. It can have two states. We've got two types of messages. So depending on the value of the bool, we'll have either a request or a response. So now our strategy is to specialize this class for requests and responses. Here's the specialization for the request. I've put true in for the value for the bool. All I've done is taken the same fields that we had before and just moved them in. Very simple and straightforward. You can imagine the response is going to look similar. We're just going to use the same fields. Now, people don't like to see true and false sitting naked in the code, so we can create a few type aliases. Now we have request and response type aliases to make things more friendly for the user. Okay, let's look at our serialization function. Now the serialization function takes a message. This is starting to look better. If the user tries to pass a foo, the compiler will know you can't pass a foo to this function. You can only pass a message that is either a request or a response. So we're making progress. All right, next problem we have is our container's not allocator aware. So what can we change in this declaration to allow the user to specify the type of allocator used for each of the elements, each of these data members that needs an allocator? Just think about the answer. So if you thought add an allocator template parameter, hey, that's not a bad idea. Let's see what that looks like. Okay, so this is that. So now, you can see I've chosen to use the same allocator for method and target to cut down on the number of allocators. It's a pretty reasonable choice. You might think those strings are going to be roughly the same size. Not a bad compromise. But we don't want to use the same allocator for the body. The body might be hundreds of megabytes, or it could be tiny, who knows. We don't necessarily want to use the same allocator. Now, the fields are a problem because we have a container that wants to allocate memory, and the elements of that container themselves want to allocate memory. So how do we tell this map that we want the strings inside to use a particular allocator? Scoped allocator adapter to the rescue. Here's the scoped allocator adapter, and it's going to propagate the allocator inside whenever the map creates elements. It's going to work. Now, show of hands. Who thinks this is a great idea? Okay, I don't see any hands up. You're absolutely right. This is a terrible idea. If you're working at a company and you're making this container, your coworkers are not going to be very happy with you. They're not going to be pleased. If you're creating an open source library, you might find you're not getting as many downloads as you thought. People are going to think this is overly complicated. Now, here's an interesting data point. If you search for scoped allocator adapter on Google, you're not going to get a lot of hits. Now, we need to be careful interpreting the meaning of this data, but I think it's clear that in terms of Google doesn't find many hits for it. Okay, so we're just going to put a pin in the allocator problem. It's very difficult to solve. Maybe after we do some refactoring, we can revisit that. Okay, so let's talk about customizing the body. We want to allow the user to choose different containers for the body. This is one of my favorite quotes. All problems in computer science can be solved by another level of indirection. So, how can we modify this declaration? How can we change this request container to allow the user to specify the type for the body? I want you to think about the answer in your head. So if you thought add a template parameter, well, we see how well that worked out last time. But in this case, maybe it's not so bad. So I'll just add a body template parameter. Now we'll change our string to be that type. So now you can put a string there if you want. You can put a vector there if you want. So let's see how that plays out. Here's our message class template declaration. You can see I've added the body parameter. Okay, now it's in there. Here's our aliases. Now instead of being normal aliases, they are template type aliases. They're parameterized on the body, so the user has to specify the body when they use the request or response aliases. Not so bad. If I have a request that uses a standard string for the body, I can assign a string literal. Very nice. If I have a response that uses a vector of char for the body, I can assign an initializer list of char. Okay, great. Now, let's look at our serialization function. I've changed the serialization function to accept the message with the body parameter. So now that function can accept any message no matter what body type it uses. It's a very nice generic function. So you're probably wondering, well, how are we going to implement that thing? So it's time for us to look under the hood and figure out how that serialization function is going to work. So if you remember what I said earlier, an HTTP message consists of a header followed by a body. Our strategy for serializing will be to first serialize the header. We'll call this function. We won't worry about that, pretend it's written and already exists. We don't need to get into the weeds on that. So that's done. Now we're going to serialize the body. So we call the standard OStream write function, which accepts a pointer and the number of bytes. Now, so we're going to send that data over. It's going to output, and it's going to be great. So if we have a request that uses a string for the body, and we can call write on cout, it's going to work. If we have a response that uses a vector of char for the body, we can call write on cout, and it's going to work. Now, if we have a response that uses a list of string for the body, we can call write on cout. And hey, wait a minute now, what are you trying to do here? There's a big problem with this code. Does anyone see what it is? Anyone? No data. There's no list data. What are we trying to do here? And then list size, that's not going to do the right thing. That's going to tell you the number of items in the list, not the number of bytes. So that was cool. The template parameter was cool, but it's clearly not the one. So we need to fix it. It might not be apparent, but there's a lot of other problems with this approach. For example, if we assign a string literal to the body that uses a string, we can call write. It's going to work great. But what if we want to serve a file? HTTP servers deliver files all the time. It seems like useful functionality. We don't want to leave that out. So maybe we want to put the path name in the body and then have our serialization function stream it out. But this is not going to do the right thing. You're just going to get the name of the file in the output, which is not what we want. We want the actual contents of the file. Okay, we got more problems. So if you look at this code, I told you earlier that a body is optional, so we can represent that with an empty string. But even if the string is empty, the size of our container did not get any smaller. We're still paying for that standard string even though it's empty. Now in C++, we have this mantra of paying for what you use. So here we're paying for the storage even though we're not using it. So that's not very nice. But it doesn't stop there. If you look at the serialization function, we're calling write, but we're passing a size of 0. So that call is completely unnecessary. There's no body, but we're calling the function anyway. Now you might think, hey, what's one function call? But that's not how we roll. We can't have people using other languages sneering down at us for our high-level abstractions because they're paying an unnecessary runtime penalty. We want to have our cake and eat it too. We want to have a zero-cost abstraction, and that's how it is. So how can we fix it? Think about the answer in your mind. If you thought about adding another level of indirection, you got it. So we're going to add another level of indirection here. Here's our declaration for the request. You can see we have the body template parameter. That's the type of the body. How can we change this to add a level of indirection? The answer is simple. Rather than using the body template parameter as the type for the container, we're going to use a nested type called value type as the type for the container. So now we're no longer instantiating the body type. We're just using it to name some other type. This is a little bit abstract, so let's see how this plays out. Here I've created a user-defined type called a string body. It has a nested type called value type, which is a standard string. If I declare a response that uses the string body, I can assign a string literal to it. Okay. Here I've created a user-defined type called a vector body, which is templated on some element t. It's got a nested type called value type, which is a vector of t. I can declare a response using vector body of char, and I can assign my initializer list of char. So, how about the list? Here's the list body. It's got the nested value type. Now we can declare a response that uses a list of string. We can assign our initializer list of string literals, but we have a problem because the serialization is not going to work. So we've added a level of indirection, but we didn't solve the problem. What happened? I thought adding levels of indirection helped. Well, it does. All we need to do is add another level of indirection. We're gonna be rolling. So how do we do that? Here's our serialization function. You can see we're calling os.write. That's where the problem is. So how can we fix that? So we're going to change it to call a static member function of the body type. So what does this mean? We're going to delegate the responsibility for serializing the body container to the body type. So once again, notice that the body type is not actually instantiated. We're just using a static member function to solve our problem. So now we just delegated the problem elsewhere. In order to do that, we actually have to have an implementation. So here's a user-defined type string underscore body. You can see I've added the static write function, which does the right thing. We send the container to the output stream. Now we can declare a response that uses a string body, and it's going to serialize correctly. Can we solve the problem of the list of strings? It turns out that we can. Here's our list body. We've got the nested value type, and now we have a static right member function, which does the right thing for the list. We loop over each element, and we send it to the output stream. Now, there's something really cool about this, which is this will not only work for strings, but it will work for any type that supports streaming to the output stream. So we just got a feature for free. It's very nice. Let's revisit the problem of the optional body. So can we create a user-defined type called an empty body that lets us have a zero cost? Well, it turns out that we can. Here's our empty body type. You can see we've got a nested value type that has no data members. Now we have our static right member function it's inline, class definition is in there, and it doesn't do anything. So when the compiler generates the serialization function and it calls this static function, it's going to optimize to nothing, so we're paying no runtime penalty. We have a little problem though. The size of that body member can't be 0. In C++, there's a rule. The address of any data member of a class must be distinct from the address of every other data member. So we still want to pay nothing for this, so we're going to have to do a little bit of refactoring. The first thing that we're going to do is we're going to eliminate the body data member, and we're going to replace it with a couple of accessor functions. These accessor functions will return a reference to the body, const or non-const. So how do we implement this? So there's a feature in C++ called the empty base optimization. If a class is derived from another class, and that other class has no data members, then it does not add to the size of the derived class. So we're taking advantage of that here. We're deriving our message from the body value type. We're using a private derivation so that the user can't see the derivation. They can't see the hierarchy. And now our implementation for the body member function just returns the body portion of the message. Very simple. Now, this adds a lot of boilerplate to the slides. I'm showing you this to show you that abstractions can be zero cost. We're just going to continue with body as a data member to avoid having too much code up on the screen. Okay. Let's revisit the file. Now do we have the technology to serve a file simply by putting a file name into the body member? It turns out we can. Here's our file body. We've got the nested value type, which is a string. We've got our static write function, only this time the implementation of the function opens the file, loops over the data, and delivers it to the output stream. Now there are two interesting things about this implementation. The first one is that the body value type up until now, it's been a container of bytes that actually get delivered. But in this case, the meaning of the body is now a file name. The file name is not delivered, but the contents are, so the semantics have changed. The implementation of the write function up until now has been to deliver everything that's in some container in memory. But in this case, we don't have the entire file contents in memory. In this case, we're just delivering it 4 kilobytes at a time. So that's a really cool feature that came out with our design. That's an indication that we're on the right track. So, I have an announcement to make. We've just created a concept. That's right. Body is a concept. So what's a concept? If you have a given template type, a concept will define the syntactic requirements. In other words, what is necessary for the correct compilation, as well as the semantic requirements. What do you need in order for the program to have the correct behavior at runtime? All of the types that we've created are instances of the body concept. They meet those requirements. Now, it turns out everyone here has already been using concepts. If you've called any of these functions in the standard library, such as find or sort, the objects that you pass meet certain standard requirements, such as input iterator or less than comparable. So, now let's talk about documentation, that thing that everybody loves to write. So, if a user sees our message container and they need to create an instance of this type, chances are pretty good they're going to know what to do with the bool. They got a 50-50 chance of getting it right. Hopefully they know they have to put true or false there. But when it comes to the body, now things are not so clear. What do they pass for the body type? If they're using the request or the response alias, they need to provide a body type. So how do we inform the user of what kind of types that they can put there? And if the user wants to create their own types, what are the requirements? For that, we need documentation. I'm going to show you 2 forms of documentation. The first is called an exemplar. An exemplar is a piece of valid C++. It's a declaration that contains all of the elements necessary for the concept. However, it omits the definition. Here's the body exemplar. The name is body to inform the user of the concept. It's got the nested value type, which is a forward declaration. It's got the declaration for the write static member function. and it's got some comments that tell you what to do. Now, why is this useful? Well, the user can take this and they can copy it and they can paste it and they can rename a few things and add their code and then they can go. Now in this example, it's small, maybe that doesn't mean so much, but if you have a concept with a lot of requirements, 20 or 30 member functions, you're saving them a little bit of time. Also, people understand code. I mean, hopefully programmers understand C++ code when they see it. So a piece of code is going to speak to programmers more easily than exposition. The next form of documentation, which is more formal and more prevalent and what you're probably used to seeing, is called the valid expression list. The valid expression list shows you all of the valid C++ expressions that are associated with the concept, as well as their semantics. Here we've got our symbols. B represents some type that we want to confirm that it adheres to the concept. And then in our table, we can see B has to have a nested type called value type. In the description, we explain the thing that it's supposed to be or do. B has to have a static write function with a particular signature. The description column is the place where you put all of the information required for the specification. Your post conditions, your preconditions, the exceptions, safety guarantees. If you have any algorithmic complexity requirements, those would go there. And of course, the explanation of what to do. Now, this documentation is great for users, but it doesn't help the compiler. You can't take this and feed it into the compiler and then have it help you determine if your types meet the requirements. So we need to do something to allow the compiler to be informed if a type is valid for our needs. And to do that, we're going to have to dive into some metaprogramming. So I'm going to show you some metaprogramming. The techniques that I'm going to show you are not state-of-the-art. They don't represent all of the latest and greatest. They're just some meat and potatoes C++11. My goal in showing you this is not to make you walk out of here as metaprogramming experts, but just you have an idea of how this sort of thing is done. Having an understanding of the basics will help you in some situations. For example, if you get a compiler error and you know the fundamentals, then maybe you'll have a better chance of figuring out why it's not working. So we would like to write a meta function called isBody that determines whether or not a given type meets the requirements of our concept. Now, you've probably used these things before in the standard library. You've got isReference, you've got isConstructible, that sort of thing. So we're going to write something like that. Now, why would a meta function like this be useful? Well, if a user passes a body type that doesn't meet the requirements and they try to compile, they might get a really big error. They might see a message that has nothing to do with the real problem. So one of the uses is to create some diagnostics for the user. If a user tries to call this function and their body doesn't meet the requirements, they're going to get a nice message. It's going to say body requirements not met. So this is a mark of professionalism for your library. Users are going to thank you. People like to see this sort of thing. It's extra polish. Another purpose for meta functions is to use with enable if. If you want to constrain a function so that it only appears in the set of candidate overloads, when the type meets the requirements, you can do that. So this is another tool in your metaprogramming toolbox. So we're going to write it. Now, in order to write it, there is one thing that we need, which is so incredibly useful that we just have to have it, and that is void underscore t. Void underscore t maps a series of 0 or more types to void. You're probably thinking, what use is that? But trust me, it's going to come in handy. If you don't have access to C++17, you can just copy the implementation. It's that simple. It's just those 2 lines. If you're using a slightly older compiler, you might need to add another 2 lines. You can find those on the internet to work around a little defect. Most of you probably won't run into that. So we want to create our isBody meta function, so we declare the primary template. Here's B, which is the type that we want to test. And then we have a second template parameter, which is defaulted to void, and we're going to use that in our specialization. The primary template is derived from false type, which means that by default, any B is going to immediately be considered not valid. Our strategy now is to specialize this class for the case where B is valid. And the way that we do that is we introduce the void T. Inside the brackets for the void T, we're going to put a comma-separated list of expressions which must be syntactically correct. Now, you have to understand what SFINAE is. Substitution failure is not an error. That means if the compiler substitutes a B, which would result in a compile error, inside the brackets of that void T, rather than aborting compilation, it will simply discard the specialization from the set of candidates, and it will fall back to the primary template. That's the behavior that we want. So first we want to check for a value type. All we do is we name the type. So you can see type name B value type. We put that in our list. So now we're checking for value type. That's going to be great. So we're halfway done. The next thing that we need to do is check for a static write function. Our strategy is going to be to call the function. Now, we can't actually call the function, right? This is a context where we're expecting a type. So we're going to use the decal type keyword to tell the compiler to give us the type as if the function was called. So here we introduce decal type, we call b write static member, and then we need some variables to pass in the parameter list, otherwise it won't be valid. Here we're going to use decalval, a C++11 feature. Inside the template parameter, we name the type that it has to be in order for the signature to be correct, and that'll give us a type that's going to be right. So if b has that nested write function, then isBody is going to derive from true type. Otherwise, it's going to derive from false type. Don't ask me about the void 0. It just has to be there. I'm not really sure why. I'm guilty of copying and pasting code from the internet to get things working. Don't look at me like that. I know you've done it too. So you can find this code in my GitHub. You can see that it compiles. So what have we done? Let's take a moment here and figure out what we've done. We've created a generic algorithm. Our serialization function is a generic algorithm. The parameter that it accepts meets the requirements of a concept. A concept has to be well documented because the compiler's not going to tell you what it's supposed to do. So we've got the documentation, and we have our meta functions to inform the compiler if a type is going to meet the requirements. So here's that serialization function that we wrote. Now, if you remember, early on in the talk, I talked about the algorithms that we want to perform on the container. We wanted to serialize a message, but we also want to parse it. So can we create a signature for a parsing function that uses a standard input stream and writes the result into the message? It turns out we can. So here's an implementation. It looks very similar to write. The first thing that we do is we read the header, and then we delegate the responsibility for reading the body to the body type. So now we need to add to we have our string body class here. We're adding the static read function. The implementation is very simple. We extract the string from the input stream. But wait a minute, now we've just added to the requirements. So we need to document that. So we go back to our valid expressions list. I just add a row. Here's the row for read. You can see in the description it tells you what it is that it's supposed to do. But now that we've added to the valid expressions, we need to inform the compiler. So we go back to our meta function, and then we just add another item in the comma-separated list. So you can see that this is extensible. As you add more requirements, you just put them into the trait, or you put them into the rows for your valid expressions table. You just need to be diligent and orderly about making sure that your concept is well specified. Now, let's revisit the problem of allocator awareness. So do we have the technology to solve this problem? Well, it turns out we actually have already solved the problem for the body. If we have a vector body, we can just add an allocator parameter to that type, and now when the user declares a vector body, they can specify the type of allocator. However, we have a little problem. Let's say the user has an allocator called myAlloc, which is stateful. In other words, it requires parameters upon construction. It cannot be default constructed. Our message class doesn't have any constructors, so there's really no way for us, with the declarations that we have so far, to initialize that object. That's no problem. We just add a forwarding constructor. We use perfect forwarding. Any parameters passed to the constructor of the message will just be forwarded to the body container. Seems like a reasonable thing to do. Now, body is now allocator aware. Let's look at the fields. So the problem with the fields is that we're stuck with a map and we don't have any control over the allocator. Is there something we can do to change this declaration so that we can get that level of customizability that we want? The solution that I chose in my library is to simply add another template parameter called fields and then derive the message from that type. Seems a little weird, but you'll see why this works out. So we've created that derivation. Let's revisit our primary template. Here's a message class. Now I've added the fields type to it. Here's our serialization function. I've added the fields template parameter. Our serialization function can now accept any message that has any type of body and any type of fields. Now, the user has to know what to put there. We've gotten rid of the map. We need to replace that missing functionality. We need an implementation of fields that does the things that we need to do, such as insert values and retrieve values. So what we'll do is we'll create a new user-defined type called basic fields that's templated on the allocator, solving our allocator problem. And here's a couple of member functions. This is just a minimal implementation. You can imagine you can add more to this interface. To give the user some convenience, to save them some typing, I create an alias that uses the default allocator, and now we modify our request and response aliases to use that default. So now request and response are backwards compatible. If you don't name the fields, you get the default fields with the default allocator. You can specify your own fields type if you want, including a basic fields that uses your allocator. Very nice. The constructor, you can imagine, we just add to our forwarding constructor and we pass some parameters to the fields as well. I won't get into those details. Now, what does that look like? So if you have a request using a string body, now we can set a field. We're setting the user agent field to the value Chrome. If we want to retrieve a field, here you can see we're applying the array index operator to the request object. Notice how it looks like set and array index are members of the message. The reason that it looks that way is because we've derived message from fields. So this is like a neat way to extend the interface of a class. This is something that's a little off the beaten path, deriving from a user-defined type and a template parameter list. So at this point, you're probably thinking, wait a minute, we just added another concept. We just added fields. What the heck is that? So we need some documentation. So we're going to create a valid expression list. Only this time, you'll notice that those member functions, they're not static members anymore. These are members of an instance. So in our notation, we have to have an instance in order to form a valid expression. So I've added some terminology. F and C are instances of some candidate fields type. We have the parameters N and V, which are the strings that you need to pass into that function. So that's our valid expression. Now, here's where we're at. We have the allocator awareness for the body. The fields can be customized. The user can choose the implementation. They can choose the allocator. Now we're down to one hard-coded allocator. We have one standard string that uses the default system allocator. How can we change this declaration so that even that string now is customizable without adding an allocator template parameter, of course? So the method that I chose is first, we're going to refactor this class to eliminate the data member. I've converted over to string view. Now there are some people who think that string view is harmful. That could be the subject of another talk. So I've added accessor functions for the reason string. How are we going to implement them? Here's an implementation for those functions. We're calling these new functions called getReason and setReason, which are members of the class. But these are not part of the message class, so in order for this to work, they have to be part of the fields. So in other words, we're delegating the responsibility for managing that string to the fields container, whatever it is. Now, why would we do that? Well, the fields container is already good at managing strings. It manages the name-value pairs. So it's not unreasonable to give it a little bit of extra responsibility for managing this one string for responses and the two other strings for request. Not a bad choice. So here's our basic fields. You can see I've added the two accessors. We've got the get and the set functions, and I've marked them as protected. Now, the reason I did that is because message is derived from fields. So now the user can't see those two functions. They can't go behind your back and mess with the implementation functions. That's only possible because we use derivation. But wait a minute, what did we do? We added more requirements to fields. We've got to go back to our valid expression list and add a couple of rows so the user knows what they need to put there. So here's our get reason and our set reason for the fields. You can imagine we're going to need to write a type trait for the is fields. We're going to need to have all of that in there. So now we're at a really good point. We've solved a lot of problems. We've done a lot of things. And I want to say that you're the boss. Now, what does this mean? We're all used to interacting with concepts through the standard library. Standard library's got lots of concepts. They're really cool. It's got generic algorithms. It's got flexible containers. However, the standard library is designed for general purpose computing, right? It's general purpose. It's not specific to any domain. But programmers like me and you in the real world who have to solve problems, they need to create the class employee record, or they need to create the class invoice identifier. They don't have the luxury of designing vocabulary types like vector. So when you're going to create these concepts, you're going to have to encapsulate a lot of little really annoying business rules that don't fit neatly into things like move constructible. And it helps to be able to have techniques that will let you do that. Now you'll notice the techniques that I used are not found in the standard library. I have derived a class from a user-defined type. I've used static member functions of a user-defined type. And the reason that I did that is I want to show you that you can think outside the box. You can use any of the language features so that you can create a custom solution that works great for your domain-specific use case. So at this point, I'd like to summarize the talk. Here are most of the declarations that we talked about. If you have any questions and you want to reference them, that's very nice. All of the code that I've shown you, it compiles. Don't worry, I didn't put up code that's not going to work. I checked it before I came here. You can access the repository and you can see what's in it. You can access the slides. They're in a PDF file, so you can look at that. There's also a wonderful page on the Boost website that discusses generic programming. It overlaps a little bit with some of the things I've talked about. It also has some other interesting ideas that you may find helpful if you want to continue your journey on education into concepts. Now, if you want to talk to me and ask me any questions on any subject at all, I have a very light schedule. I'll be here now, and I'll be around the conference for the rest of the week. And I'll also be appearing tomorrow night at the Meet the Speakers dinner, which is a paid and scheduled event. So if you'd like to sit down with the speakers, not just me, but all of the speakers, you can do that. You can register for it, and we're going to be there tomorrow night. So, in closing, I would like to say I'm very grateful to the people that have put this conference together, John Cobb especially. They've given me the opportunity to bring my ideas to you and share them with you. Can we give them a round of applause? Thank you. Okay. The dreaded questions.
Great talk, by the way.
Thank you very much.
My question is about the static assert you put in to make the error message nicer if the body doesn't match the concept, using the type trait that you defined. Is that actually what you use in Beast, and does it help users to give them a message that's so broad, just saying their type doesn't meet the requirements? Because if you didn't have that, then the compiler would give them a noisy but very specific message about what it is that...
Okay, so the question is, do I actually use the C++11 trait mechanism that you saw on the slides in the actual library Beast? Actually, yes, that's what I use, and I keep it at C++11 because there's still a lot of people using C++11. It is actually helpful. When users stick to the types that come with Beast, of course, they're not going to have any problem. But as soon as they create their own type, they're going to get that message. And the documentation in Beast is very explicit about what the requirements are. So they can go back to that documentation and check it.
So you're finding that users find your documentation more helpful than the compiler's verbose error messages?
Absolutely, yes. The feedback has been overwhelming that having the additional diagnostics is useful. That's one of the things that came out during the Boost review.
Great, thank you.
Thanks.
Yeah, I got a question regarding your use of the body and the field structures, where you said that you passed the additional arguments to your constructor to the body constructor.
Right.
Now, you said you could do the same with the fields constructor, but how do you, how do you know which of the arguments that are passed go to the body constructor and which go to the fields constructor?
Okay, so the question is, when we added the fields as a customization point, how do we now have constructors which can route 0 or more arguments to the body and 0 or more arguments to the fields? Is that the question? Yeah. Okay, so I could have put that on a slide, but it would have been a really big slide. The solution that I chose is just to copy the interface of pair, right? Because pair solves that problem. Pair has a whole bunch of constructors. It's got a single argument constructor. It's got 2 argument constructor for initializing each of the members. And then it has something called a piecewise construct. So if you use piecewise construct tag, then the second and third parameters are tuples. And that tuple can be forwarded. Now, of course, that would be too much for the slides. You can see that in Beast, by the way. Beast has if you want to see the body concept and the message container in Beast, it's much more full-featured. It solves all these problems. You can take a look at it. You can look at the documentation and see how the concepts are actually specified. There's more to it. What I've done for this talk is I've dramatically simplified it so that the slides will fit and to not overwhelm the audience.